Okay, so 2. 2 is a natural number. That was the first natural number we came up with. As soon as somebody had more than one sheep, they said, oh, got 2 sheep. Okay, so 2 is probably the most natural of the natural numbers. It's an integer because the integers consist of the natural numbers plus 0 plus all the negatives, and that's certainly one of the integers, positive integer. It's rational because we could express it as 2 over 1 or 4 over 2, etc. We could express 2 as a ratio of 2 numbers, as one number divided by another. And it's also real because, of course, all these categories are part of the real numbers. -5 is an integer, okay? It's one of the integers we got when we got around to adding the negatives into the set of integers, or considering negative natural numbers, the negatives of the natural numbers, and adding those to our set of natural numbers plus 0, our set of whole numbers, we got what we call the set of integers. Okay, and it's rational because it can be expressed as -5 over 1 or 5 over -1, for that matter, -10 over 2, 10 over -2, infinitely many different possible ways. And don't know how this got smudged, but it's also real. When I moved the board, I must have grabbed it there. Okay. Square root of 17. Now, we can't prove this. I can't explain to you why. I could explain to you why. I could prove it, but we don't want to do that in this course. It's simply, it's not natural. It's not an integer, and it's not rational. Okay, it's clearly not natural. Square root of 16 is 4. That's natural. Square root of 25 is 5, that's natural, and of course both of those would be integers, but nothing between 4 and 5 is a natural number, so the square root of 17 being between 4 and 5 then would not be a natural number. It's not rational, okay, and that's what I can't explain. I can't explain to you why it's not rational. I could explain it, as I said, but I'm not going to do that in this course. Okay, but it's not rational. The square root of an integer is not rational unless it's a whole number. Okay, so square root of 16 is rational because it's 4. Square root of 25 is 5. That's natural, but that's the only way a square root of an integer can be a rational number. Okay, so square root of 17 is irrational, and of course irrational numbers are part of the real, so it's real. Okay. Negative 1.3434 repeating is rational. You remember from long division, I hope, that frequently you'd get a long division where your answer started repeating. It started repeating because you got the same, you brought down the same numbers that you had brought down before. And it turns out that, and I could again prove it, it's not hard to prove, but it turns out that any repeating decimal is a rational number, okay, just like the repeating decimals you got when you divided a whole number into a whole number. And it's also then, of course, real. 5/8 is rational and real. I haven't even, if we wanted to get 5/8 between 0 and 1, we could divide the interval into 4 parts, and we could locate something like 3/4, and we could divide each of these parts into half and count over 5 of them, and we would have 5/8. So it's rational and real. Pi, as you should know, is irrational. It goes on forever, but it never repeats the same numbers. There's no point from which it starts repeating the same numbers over and over and continues doing so forever. It's irrational. It's real. Okay? And pi is irrational. Pi over 4. If you divide an irrational number by a whole number, it's still going to be irrational. And then the number 5.4343343333. Now you have a pattern here, and it's not exactly a repeating pattern. Okay, I kind of said it was. But it's not a repeating pattern. It's just a pattern. And there is a degree of repetition in it, but it's not actually a repeating pattern. But it's not the same numbers that keep repeating. There's an extra 3 with each time this thing goes through what you would perceive as a cycle. So, it's irrational. And of course, it's real.